very much. It's really a wonderful pleasure to be here today with you today. It's the first time I have really been to Amsterdam. In fact, after living in Europe for over nearly 2 decades, I never really made it to the Netherlands. And so I'm super, this is the first time that I made it this far. And I've always been wanting to come here because you guys do amazing, fantastic work that we treasure and appreciate greatly in Hannover. And yeah, sadly, it's going to be a short stay, but I hope it'll be the first of many. So thank you very much for giving me the opportunity to talk to you today. I want to tell you only simple and trivial things today. The background for this is I've been, in the past couple of years, drawn into the nexus that is the quantum, whatever you want to call it, revolution that's happening right now. And in Germany, it's been particularly active. A lot of investment has been made available in Germany for quantum computing and applications. And I was drawn, just because I couldn't say no loud enough and fast enough, I was drawn into this, and I ended up working on some industry academic projects. So I actually had the misfortune to coordinate a consortium of industry and academic partners. It's been an amazing learning experience. And I wanted to share with you some of my learnings today. Like, this is the learnings of 3 years of working on quantum computing and industry together. And I called it assessing quantum advantage for interlinear programs because that's kind of what we wanted to do. We wanted to answer, I mean, 2-3 years ago, when we started talking to industry partners, they would always ask us the same things, you know, like, can we have quantum advantage now for our use case? And we would always have this patient explanation where, well, we don't quite have quantum computers yet. Blah, blah, blah. And then after this period of disillusionment, I think we found some interesting and productive way to work together. And there are some things that I could share with you. But I want to start this talk by just with a bit of reminiscence. So I've been in the game for about 20-something years now, and this was my first big conference that I ever went to in quantum computing. It's QIP. It was held in Canada at the Perimeter Institute. Well, no, it wasn't, because the Perimeter Institute wasn't even there. It was held in a separate building, 2004. And in this picture, I think you can see more or less most people who worked in quantum computing in the world. Okay, it's not everyone, but I would say a fair percentage of everyone that was active in quantum computing in 2004 is in this picture, with the exception of maybe 20% of the practitioners. This is from gut feeling.
What building is this?
This is a there's this weird distillery building. It was a.
Or is it like the CC?
I don't remember the name of the building, but they drove us in a taxi bus to some place where they made whiskey.
Is that Charlie Bennett who kind of?
Yeah, they're all there. Yeah, there's Peachful there, Barbara. They're all there. And we were all together, and it was an amazing experience. And especially as a very, very young student at the time, I'm right in the middle, barely recognizable. And at the time, we were very excited about quantum computing. But at the time, I also want to point out that there was a distinct lack of anyone to do with industry or anything like that in that photo. It was a largely academic pursuit. It was somewhat mocked by even more sober and serious physicists, which is a bit of a contrast to what we have today. I did not go to QIP in Taipei, but that's a picture of the event. And I understand it was a mega event with multiple parallel. Did anyone go, actually? Was it a mega event with parallel sessions and industry partners and things like that? Yeah, right? So it's not even possible to probably make, I Googled, can you make a picture of all the quantum information people in the world? It wasn't possible. So the estimate was 1,600, but I think that number, the number of people who call themselves quantum computer experts now, is probably more than what can fit comfortably in a picture, right? You know what I mean? You know what I mean. So it's a funny way. The world has changed and the priorities have changed. So in 2004, our priorities were about, really, people were obsessed with exponential speedups, provable exponential speedups for problems like factory, like hidden subgroup problem, very, very academic problems. And now people are obsessed with other things. And how was that reflected? Well, the funding was in 2004 was 0. Well, I mean, there was Mike Lazaridis, so the funding was not 0, but now the funding is insane. 173 billion according to McKinsey.
If McKinsey said it was small, then no one would pay for their consulting
That's
services.
indeed
though.
true. So it is, but this is, I can definitely, in Germany, it's 2 billion, right? Germany has invested 2 billion in quantum computing. And this is potentially the beginning of maybe an S-curve in investment. Maybe we're going to see a lot more growth and development in quantum computing in the next years. And so that's sort of brought with it its own challenges and fascinating opportunities. For example, in 2004, we were really, I would say, quantum computing development was motivated by theory, by complexity theorists. They were the people driving the narrative in the community. People like Pete Shaw would be driving the narrative, talking about hidden lattice problems, things like this. Nowadays, the narrative is taken away from us. As academics, we no longer have any agency in how quantum computing is developing as a field. You probably experienced that. They don't know, no industry, major industry thought leader really knows the main players academically in quantum computing. And that's a problem. It's a problem for us to address. And how do we address it? I don't know. I'm just going to throw it out there and just say, I think that's a problem, and I don't know how to solve it, except by talking to thought leaders, maybe becoming a thought leader. So yeah, it's a thing, but I think we could still meaningfully contribute and answer some big questions, right? Because that's what brought us into the game originally, I guess. Like, let's start with some of the big questions where I think there are no actual real good answers yet. So, the first one and the most serious one for this talk is, where are all these quantum software solutions? People are implementing them all over the place, solving problems on quantum devices. But what have we solved? What class of problems do we routinely study with quantum devices? You know the landscape of the literature. I don't have to tell you that. And then, but there are bigger promises made to industry. Where are all the polytime algorithms for NP-complete problems? And then there's even bigger ones that politicians have heard about. Why haven't we cured cancer yet? And why can't I upload? This was seriously said by the Minister of Science in Germany. Why uploading your brain to a quantum computer? These are the big questions that people expect progress on, right? Industry partners, if you talk to them, they'll give you somewhere on that scale these questions, and you have to answer that. But you all know the answer, right? I'm preaching to the choir. It's hard, it's subtle, it's nuanced. What does it mean? Quantum advantage. How are we going to get these mythical solutions? Well, it's not easy. It's not even easy to explain what we mean by the words quantum advantage. I'm not really going to attempt to do that because you know what I mean, right? I'll say a couple of brief words. I would consider something quantum advantage to have been demonstrated, and therefore, quantum computing's place to have been cemented, if we have a faster solution than the best classical algorithm for a useful problem, a better quality solution for the versus the best classical algorithm for a useful problem, a greener solution. Maybe it's slower, worse quality, but it's greener. That would also be quantum advantage for a useful problem. Or, yeah, we'll be permissive of what we mean by quantum advantage in this talk. That's what we're chasing here. That's what the industry partners really want. And the minute that's demonstrated, and everyone will know when it's been demonstrated, it won't be some paper in Nature. We will all know when there's true quantum advantage. Then we may expect investment to really go exponential for a while. And then who knows what the world will look like then. But I'm still very interested in the question of just sort of predicting or understanding when quantum advantage for a useful problem might happen, or can we already dismiss it and say, no, it's never going to happen. Maybe we can. And I'm not going to hold you in suspense for my whole talk. I'm going to give you the main message straight up. And I think this is an interesting learning. It's an incredibly simple observation, the one that we took 3 years to painfully make. But it's one that I found sufficiently surprising, comparing my mental status 3 years ago to now, that I think it's worth sort of sharing with you. And the main message is this. If we just care about Grover-based speedups, for integer linear programs, and I'll go into details of these words, these can differ wildly, and it all depends on how much initial classical side information you give Grover. And this should become, as I talk, the most blindingly obvious statement, but the actual implementation and measuring of how much usefulness you get from side information should become maybe surprising by the end of this talk. So that's the main message, and we're going to sort of circle around this main message for the rest of the talk. Okay, but before I do that, I want to step back. Quantum algorithms they're really hard. They're really hard. Like it annoys me how hard it is to discover quantum algorithms. Like 20 years ago, we were talking about the hidden subgroup problem and the Fourier transform. You know, we had the last sort of big one was HHL linear systems, right? Maybe arguably there's been other quantum algorithms since then. I don't want to pretend there's been no new quantum algorithms, but it's really hard to discover these things. And it's very annoying, it's very frustrating because it should be easy, shouldn't it? And so I want to contemplate for a moment why is it so hard to discover quantum algorithms? And I want to say some reassuring words because I want to draw a parallel with the development of classical computers and point out that I think we've got reason to be optimistic. And so I'm going to start by answering the question, why is classical software development easy? Not why quantum is hard, but why is classical easy? Well, let's zoom back in time, go back to the 50s. If you were interacting with a computer in the 50s, it probably had vacuum tubes in it. There were some semiconductor components in computers at the time. They had diode-based switching, but they did not use transistors. They used vacuum tubes for the logic gates. Here's a classic IBM 604. I think that had 48 bits. I can't remember the details. A couple of 100 bits of RAM, which was on a spinning drum. It was incredibly noisy, loud, failure-prone, and hard to program. Does that sound familiar? Hundreds of bits. It's kind of the space we find ourselves in now, isn't it, with quantum devices?
I would kill for an IBM 604.
I would find an IBM 604.
It's about 10 years ahead of what we are right
It's
now.
still a bit ahead, right? Yeah. But it's not that, it's sort of the comparable phase in the development of computation, right? Noisy, failure-prone, hard to program, hard to integrate, no abstractions. Now, what do we have today? We have this. We've made computation into a commodity. It's something where you don't even know the name of the manufacturer of the computing device you're using. Yeah, sure, if you have an Apple. But do you know the name of the manufacturer who produced all the semiconductors in your quantum device, your classical device? You probably don't, right?
With high probability, it's TSMC.
With a high probability, it's TSMC or Samsung, right? So, but it could be generic. It's generic, right? What's inside. And that's enabled something. Generic computation, commodity availability of computation has enabled the software development cycle. So this is why programming is easy. But let's face it, this is not how we program, is it? Really, we just do this. And this creates the ultimate feedback loop for discovering new algorithms. You just who doesn't do this, right? Who actually sits and works out some scheme of some algorithm and then implements it? Nobody does this. They download a REPL, they start hacking, and sooner or later you work out what works and what doesn't work, and you found a computational solution to your problem. It's amazing, right? The feedback loop of interaction with a classical computing device has supercharged the discovery of classical algorithms. And we lack that feedback loop in the quantum world. That's okay. I mean, we can hope that it's coming, but I would argue this is one of the main reasons we're having a real tough time right now discovering quantum solutions. Let's just bullet pointize that before moving on. You know all of this, right? I'm again preaching to the choir. Why can't we have that feedback loop? Well, because we can't just simulate 100 qubits classically. I mean, if we could, then what's the point? Bummer. And it's hard to measure this quantum advantage when developing this, trying to instigate this feedback loop to try and discover new classical quantum algorithms. We want to measure it against good things, and the good things are classical algorithms, but they have like 60 years of progress that you have to somehow fight against if you want to prove that you've got some hope of quantum advantage. And complexity is actually a really poor measure of advantage. That's a message that you'll hear me say ultimately multiple times. Quantum algorithm research is very theoretical. I think in the past 20 years, it's probably changed. Yeah, real devices are noisy and small. And quantum mechanics is surprisingly still unfamiliar, and probably always will be. It's hard. The education game we have to play to introduce people to quantum computing is non-trivial. There's a huge barrier to entry. And I claim you need to know quantum mechanics before you you program a quantum device. Wouldn't it be great if you could just give someone a online course on quantum mechanics and then they could program a quantum device? Yeah, it kind of works. You've seen what's happened. Not really, right? Okay, real devices. I want to talk about real devices before moving on in this talk, just to set the ground rules for this talk. What are the ground rules? This is very important in any talk about quantum computation and quantum advantage. We need to say what we believe to be true or what we expect to be true or what we assume to be true, and we agree on that so that we have a common reference frame. Here's just some pictures of leading hardware platforms that have been investigated. You're probably familiar with them. Rydberg is not there, probably should be on that list. But there's the main platforms. Here's some projections of how many noisy qubits that these devices will be able to operate certain timelines. Yes, I mean, I love the guys. I did my PhD with Jeremy O'Brien and Terry. I love PsiQuantum. I do hope it's true. That's their own projections, right? This is not mine. This is their own prediction. And that's logical qubits, right? This is the last one. So this is, I hope for that reality, because then we get to just teleport straight into the future.
I think they actually pulled back from this claim.
They have
If you
pulled
can
back.
find a source online that still has this claim in there, even an old one. Please let me know about it. I would really like to have it.
Yeah, they have pulled back from it a bit. I mean, they have supply chain issues to do. So but there's something interesting to see on this picture, right? There's doubling happening. There is a visible doubling. It's a stupid metric, I know, but there's a doubling, right? There is progress in the hardware.
It better be doing that, right?
Yeah.
Otherwise we'll be here for a long time.
We're screwed if it's not doubling. But at least the hardware, I mean, this is such a difference from 20 years ago when we didn't even have one qubit. Can you imagine what it was like to talk about quantum computation when the experimentalists were like, well, we can't even entangle 2 qubits. It's a depressing game. Now there's the optimism that I perceive in the community is amazing. It's a wonderful time to be alive. Okay, so here's the ground rules. I want to talk about 3 possible futures for quantum computing, and then we'll select one so that we can move on. Okay, here's the world's most pessimistic future, stagnation, right? It's the best that we'll ever get. Somehow everything crashes to a grinding halt through global political reasons or whatever, and we never get more than what we have today. I think you'd have to be a real hard skeptic to really
Do we
think.
get to pick which of the 3 futures we?
You don't have to pick, but we just have to agree on one for the sake of hypothesis, right? So the hard quantum computing winter, is that a future? Maybe. There's another one, which I think this is somehow the scary one, and that is that we remain sub-threshold forever. And I could sort of believe that could happen if it turns out that getting above threshold is a huge supply chain problem. We just have to get our manufacturing facilities to such a level that requires such trillion-dollar investments that we never quite get above threshold. Like, it could happen. And I don't really want to think about that future. I think this is the worst outcomes. Then we've got annealers for the rest of time. No. Let's just be optimistic. And I'll give you one reason why we'll be optimistic. And the optimistic outcome is that we hit the fault-tolerant threshold somewhere in the near future. We get to have logical qubits and logical gates. It's very crucial for this talk. And how many? Well, at least hundreds to thousands, maybe millions, maybe billions of qubits, logical qubits. And also, kind of important for this talk is that logical gate times get down to at least, say, 10 to the minus 6 seconds. You'll see why that becomes very relevant. Gate times are important. Logical gate times. To give you a sense, the limits by relativity on classical gate times are in the gigahertz, so 10 to the minus whatever, 11 seconds or so. That's just like the time it takes light to propagate from one end of your chip to the other. That dictates the fastest gate time you can have, effectively, right? Now, 10 to the minus 8 is well below this relativistic cutoff, but isn't it fascinating how computational clock speeds have hit the gigahertz level and they're not really going to go any further because they can't. There's RF reasons why it won't ever happen, and there's relativistic reasons why it's not. So this is why 10 to the minus 8, I would call that optimistic but modest, and 10 to the minus 6 will take.
kilohertz is counted. Are you not almost at this? Like, let's say that a logical qubit costs roughly 1,000 qubits.
Yes.
Then you are basically at 10 to the minus 11, right?
Mhm.
Because you're talking about logical gate times here.
Yes, it's true. Yeah, I'm being very optimistic. So this is the most, not, I think you could be a tick more optimistic, but let's just say this is the most optimistic future I could imagine, although there could be more qubits. Yeah, that's it. Let's agree for the ground rules for this talk that this is the future that we're headed to. Because it's a different talk if I select a different column, right? I'm not going to give the talk at all if it's column 1, and column 2 is a different world altogether. But I remain optimistic that we could be on the third column. We could be. And this is why I'm optimistic, right? I spent a long time looking into the history of classical computation. It's a fascinating subject. And you see that it was driven by continuous S-curves of innovation in hardware. You know, they had one hardware platform and they eked out all the innovation they could before they jumped onto the next hardware platform. You know, germanium and silicon and gallium arsenide, all these hardware platforms gave us S-curves of innovation, which added up to what looked like an exponential over 70 years. Where are we right now in the quantum world? We're somewhere here around 1951. The first transistors are being produced. First qubits are being produced. If qubit equals transistor, then that's where we are. Can we expect 70 years of qubit innovation? Who knows, right? That's too much future gazing for me. But we haven't started investing in seriously until the past couple of years.
All right, I'm coming back to the gate time one more time.
Yeah.
Doesn't it? Because there's like an error correction step, which involves like
It
this
is an error correction step.
classical chip.
That's right.
Does this not require the classical?
It requires
to go
classical.
faster than it does now.
It does, yeah. Yeah, that's absolutely right. So we can never have a gate time faster than the best classical gate.
Yeah, but even this 10 to the minus 8, doesn't it require classical computers to go faster than they can go now?
Maybe.
Because you have like this.
No, this more or less works out.
Oh,
You need about a factor of like the distance is the relative thing, right? You need, if you want 10 to the minus 8, you need to divide that by the distance because a logical gate will always take time proportional to the distance of the code. If you have a logical qubit, 1,000 qubits, it will roughly take as the distance 15, 20, then you have to divide everything by 20. And then the classical error correction needs to be at speed proportional to the error correction time. So that's like 1/20th of the logical time.
It's a fascinating discussion, isn't it?
yes.
And we start arguing about orders of magnitude here,
Yeah.
and this will become relevant. So my numbers are hard and fast and done on the back of an envelope, right? So I'm not going to defend them too hard. But I think that ballpark.
It's tight, but it works out, I think.
Yeah. Thank you. I appreciate it. Okay, so that's it. The ground rules for this talk is we're headed to future 3, and therefore all qubits and gates in this talk are logical and perfect, and there's no decoherence. With that, we'll just agree on that collectively for going forward. Let's imagine we're headed for that reality. How will we act in response to this information? And the answer is, I think we want to head to this reality where we can just sort of just hack on a quantum computer, but we can't. Okay, so that leads us to the second. No, I want that. I want to be able to just hack on a quantum computer, and I'm gonna explain back to you what I learned from you guys on how to do this. And this is what we're calling application-driven quantum software development. And I want to focus on some use cases so that we have something concrete in our minds and some measure of success and how we might get there. Okay, so one of my partners is Volkswagen. That's why I know a bit about the kinds of problems that Volkswagen cares about. So they care about optimization problems. They really do have these. They typically have production logistics and mobility optimization problems they care about. Blah, blah, blah. And here's one of their little numbers that they like to talk about. If you can, for an electric passenger vehicle, if you can just save 0.4 tons of CO2, you can save 0.4 tons of CO2 of its lifetime if you reduce its mileage by 1%. And all of my industrial partners have similar numbers like this. If we could increase the efficiency or quality of a supply chain problem solution by 1%, we save 10 million year on year. Constants matter. Constants matter. just a better quality solution by 1%, already leads to not small economic input, but actually significant economic impact. That's it, you know, like, we're not talking exponential, we're not talking polynomial, we're talking constants. If you can get a faster solution by a constant factor, you already can make a lot of money, like significant amount of money. Yep.
You wanted to go further.
We wanted to go less far. And why do we want it to go less far? Because Volkswagen has a fleet of electric vehicles that they operate. It's called Moya. And they're like Uber, right? So they have automatic routes that are programmed, that are given to them by a scheduling device. And they want those more efficient routes between passenger pickup and deliveries. Similar to logistics hubs as well.
When you say a constant matter, you mean constant, like in the quality of the solution? Not in the
That's
time
one
that it takes.
constant that matters here. But time it takes to solution also matters. So Infineon, as an industrial partner, every day they solve a huge integer linear program on a massive cluster of computers and so on. It takes them 24 hours, and that does their time to delivery for all the manufacturing plants and how the chips go into one end of the machine and come out the other. They do every day, they solve this problem. If they could halve the time, that's a constant, right? Halving, then they'd be able to solve this problem with less resources every single day.
Or like, I mean, if it takes 24 hours, is it also that they stop after 24 hours because then the day is over?
That's right, yeah.
Or maybe they could get a better
They
solution.
could get a better solution, yeah. Very fascinating, the kinds of bottlenecks that these companies have. Okay, so there's the question. Would quantum computers deliver better, faster, greener solutions? And we're going to focus on just something so we can have something to talk about. And the kinds of problems that I want to talk about are integer linear programs, because all of these problems, all that our industrial partners have, typically you have this discussion, and after about 3 or 4 meetings, you end up writing down an integer linear program, right? And that's the one that they want to solve. And it's always like that at the end of the discussion. And why are integer linear programs hard? Well, here's a picture of sort of the feasible space of an integer linear program. Linear programs are much easier because it's easier to get to the extreme points. Whereas the feasible set can be really, really pointy for integer linear programs because convex polygons sort of cut out weird, ugly chunks of the integer lattice. That's why they can be hard. And how hard? Like really hard. So also, there's something else that I learned in the past 3 years, and that is that these problems have personalities, right? They have hardnesses that are different from each other. And this is also extremely fascinating, that this thing here, this integer linear program on the right, that's fully abstract, right? That models everything. Why don't we just take aim at that? Well, the answer is some integer linear programs are harder than others. Some are considered so easy that they are also, that they're considered to be trivial or almost polytime, but others are hard. And I'm going to give you a sense of this hardness, right? Here's 3 classic problems that you always end up finding if you talk to an industrial partner. Either you have a packing problem, you have a routing problem, or you have a scheduling problem. And very invariably, you'll end up with one of these 3. And if you don't, then I'll be interested to hear from you. And some of them are easier than others. So actually, the one on the left, we're going to see this many times in this talk, the knapsack problem, that's considered to be easy. That's considered to be trivial. That's considered to be basically polytime. Even though it's NP complete, it's only weakly NP complete. So you in fact need this W to get much, much bigger before it can become truly NP complete and encode hard problems. It's considered to be the easiest kind of problem to solve. It's the hydrogen atom of optimization theory, the knapsack problem. Then comes vehicle routing. So the TSP is one you're probably familiar with. This is also considered easy in the operations research community. I'll show you some numbers in that in a minute. Like they declare victory in operations research if you've reduced your problem to the TSP. Like you know, this is not the narrative we hear in the quantum world. This is the narrative in the classical operations research world. And job shop, that is hard. That is a genuinely hard problem where even with 30 or 40 variables, yeah.
Traveling salesman.
Traveling salesman problem is NP complete, yes.
So, but then you can reduce any problem.
Aha, exactly. Yeah, we're going to get to this. I'm going to talk about this. And then the job shop problem, that is intrinsically harder than these other 2. And I'll explain what I mean by harder. Like you're like, what? Huh? It's NP complete that you can encode every other problem in terms of these. It's the polynomial overhead that kills you in that encoding. And we'll see that. Okay, So we'll focus for the talk, rest of the talk on hacking problems. They're easier. But like what I've got to say may be relevant for the others. But let's talk about them a little bit longer and what I mean by hard. Okay, you know you know these problems are hard. You know what that even means, right? Usually my industrial partners don't know these words, but you know, thankfully you know. NP hard in general. Okay, but that means asymptotically in the worst case, right? But I've just argued to you that specific instances are what matter. And so the question is, how do we solve ILPs for specific instances with a quantum device? And well, there's a challenge, right? There is no known speedup. There can't be a known speedup unless we believe in this weird reality where quantum computers can decide NP complete problems in polynomial time. There is no reality where we would have a general argument that suggests a near-term general quantum speedup.
Exponentially, you could still have quadratic speed.
We could have quadratic speedup, and we'll talk a lot about those, yeah. And so what I want to do is transition to measuring advantage, talking about measuring it and what that, because we need measuring sticks before we can talk about better. And so I'm going to give you the measuring sticks, and then we can sort of return back to what I mean by hard and not hard. So here's the standard way in operations research that you assess. Let's forget quantum for the next couple of minutes. I have one of these integer linear programs. I'm an industrial partner. I want to solve it. It has 600 variables and 300 constraints, and I need a solution by next week. That's the kind of thing that could happen in an actual real application. And you don't know what method to apply. It's NP complete. Well, that does not mean that you give up immediately. In fact, there's been 60 years of innovation in solving these optimization problems in the operations research community, and there are ways to solve it. And how do you know which is the best way? You don't, right? Because it's NP complete. You can't prove that one heuristic method, whatever, is better than another. So in the community of operations researchers, they've come to a new way of measuring which method is better than another, and it's just this. They take benchmark instances, they run their methods on those instances, and they see which algorithm performed the best. It's purely empirical science now. And that's kind of sobering, but it has led to innovation and 60 years of innovation. Let's talk about instances now, because instances matter. I've said that before, I'll say it again. Benchmarks instances are non-trivial. They have, it's not easy to come up with these industry accepted benchmark instances, because a random choice is a poor choice. That's also a key message when understanding complexity, when understanding how complicated an algorithm is. If you choose uniformly at random a QUBO, or if you choose uniformly at random a Napsack problem, or whatever, it will probably be solvable in polytime with a heuristic. Random instances are not real instances. In the real world, they're not random. Like, randomness is not around us. And so that's why there is these curated instances that people collect as libraries, and they become internationally accepted as the way to measure the hardness of a problem. Here's some examples: TSP-lib, JSP-lib, they have names like lib. You have a problem, there will be a library online, often in an incredibly annoying format, where you have instances, and they come from all places, like from some mechanical engineering plant that manufactures whatever screws versus all the post offices in the US. Like, these real instances have structure that make them hard, and they're curated, they're collected, and they're agreed on as a standard. And that's how you measure if your latest whiz-bang algorithm is good or bad. Okay, but we have a challenge, right? Because classical methods, we want our quantum devices to test them on these benchmark instances. This is the obvious answer, super obvious. But classical methods are really good, like they're really, really good. So the best methods that are out there now are branch and bound cut type methods. There's dynamic programming methods. There's SAT solvers. SAT solvers have come a long way in the past decades. They can solve enormous problems to provable optimality. Branch and bound solves these problems to provable optimality. You get a certificate at the end. This is the optimum. And I want that to sink in, right? That's so shocking. We think these things are hard, but actually these solvers, they come, they run, and they give you a certificate. And you don't need to worry that there's a better solution. You have the certificate there. And then there's also heuristics, like the power of heuristics. I've learned in the past 3 years that actually all the innovation is in heuristics. And that's the intellectual property that companies like Gurobi and IBM, they protect those heuristics with, and they're kept secret. So something like, I don't know, how many of you have heard of Gurobi or cplex? Right? Go download this program. This is insane. It's amazing. Like any problem you care about, Gurobi will solve it, and it can solve it quickly. Except when you have 600 variables. Sorry?
Maybe they have a one.
Maybe they have a Now, Gurobi runs on a laptop. It's nuts. It's nuts. And Gurobi it runs by branch and bound, dynamic programming. It has linear programming solver in there. It's got everything in this software. And it has artificial intelligence. They have neural networks now that plot the performance of various heuristics on the problem. And then they select heuristic strategies to give you better answers quicker. It's insane. It's just the most amazing thing. So I've learned that Gurobi is hard to beat, right? That's everyone in our work group. We all did you try Gurobi? Yes. Okay. And so what's to give you a sense of how hard is hard and what's easy and so on. Here's something that's also kind of shocking. So go download Concord. If you've got an iPhone, go download it. That's a TSP solver. It'll solve 100 cities, no worries, provable optimality in seconds on your phone. Gurobi can do this, but Concord is the best, right? So here's the current record, although it's starting to be broken. Provable optimality, TSP instance, 85,900 cities.
That's just the one that people published.
That's the one that people published. I mean, routinely every day, logistics companies are solving TSP with thousands of cities to provable optimality. And that's what I mean by TSP is easy. Yep.
So how do you select the problem on which you're going to solve TSP? Because I can solve it for more if it's a line, I guess.
That's right. Yeah. So usually the application tells you the problem, right? So if you're a logistics company.
But what's the record then?
This is for the US. This is all, oh, yeah, I put the picture up here. This is the tour of all the post offices in the US.
Okay, but what's the record then?
That's,
They took that, right?
I think this is the current record that's been solved at all.
What would be a better record if you had more post offices?
Yes, then, but this is not the instance that people agreed on. So people agreed on this on all the post offices in the US is the hardest problem. The current one that everyone's aiming for right now is Tour the World. That's the instance with all the cities in the world. If you can provably optimally solve TSP on the world, then you'll make the headlines. Yep.
In those encodings, do you sort of take into account that there's Euclidean distance?
Yes. Yeah. These Concord will exploit Euclidean structures, but not necessarily. Actually, the way it works is a heuristic. So Concord, the way you solve these things, it's like 80% of the computational time is proving that you got the optimal answer. Most of the time, you get to the optimal answer super quick using this K-Lin-Königin heuristic. It's a heuristic. It's not even an algorithm. They just sort of swap cities around. They do it until they get to a kind of good answer. And then the computational time isn't getting the certificate that there's no better solution. It's extraordinary, this K-Lin-Königin heuristic. This is the power of heuristics in solving optimization problems. And we're screwed, right? If we want to get a quantum computer to get a better answer, it's like it's the dumbest, naivest encoding you could possibly imagine, or even the cleverest encoding you could possibly imagine, would at least need that many qubits, right? But probably. And we're just not there yet. So what do? Well, you guys taught me what to do. It's like this paper is like everyone in our group is sort of required reading this paper here. I'm amazed that this paper hasn't become much more widely known. I'm telling everyone about this paper because you taught us how to evaluate the runtime of a quantum algorithm without owning a quantum computer. And I'm going to tell it back to you. And we've been doing this, and it's been incredibly helpful. Here we do it. Here's how you do it, right? So how would you measure quantum advantage without having a quantum device? Well, you have a classical algorithm for your problem, right? It's got some subroutines, algorithm 1, algorithm 2, And these subroutines have classical inputs and they have classical outputs. And you are like, I wonder if I replace one of these subroutines by Grover or something, if my algorithm would run faster. So you replace your one or more subroutines with quantum subroutines like this, but then you maintain the classical input and output that you're after. So the key here is that you can run the classical algorithm. If you can't run the classical algorithm, then we can't do hybrid benchmarking. So this is the key requirement. You must be able to at least run the classical algorithm for some large instance, and usually other things. And then you say, well, what if I replace the subroutine with a quantum subroutine? Same inputs, same outputs. How do I know those inputs and outputs? I log them. I run the classical algorithm and I save them, all the inputs and all the outputs in a file. And then I say, well, what if we replace those quantum algorithms? What do we need to kind of reason about the runtime of this quantum hybrid device? Well, we would want to bound the cost of the algorithm in terms of the input and output pair, right? It's very important that you have an input-output dependent bound on the gate cost of that subroutine. And then you run the classical algorithm to find those inputs and outputs. And then you calculate the costs in terms of these bounds that you've worked out with sweat and blood. Usually, I just copy them from this paper. And then you compare the quantum costs. You get a worst case bound and a best case bound for the quantum device. And then you can compare these costs with the classical costs. And you get a plot like this. So this is something that we did. We took, there's a maybe not so well-known quantum algorithm for solving simplex pivoting step in linear programming. It's by Nanachini, very fascinating paper. And it purports a quantum speedup for the simplex algorithm. The simplex algorithm, by the way, is the most run algorithm on all computational devices anyway, right? It's the most important classical algorithm, effectively, for solving linear programs. And we applied this reasoning to that simplex algorithm. So we took subroutines from Nanachini's paper and we bounded the costs of these subroutines. Often we use the most trivial bounds. So for example, if it was a Grover step, we'd say that costs at least one quantum gate. That was a lower bound for the cost. I want to give you a sense of how bad some of these bounds are we used. We said Grover needs at least one quantum gate. That's a lower bound on its cost. Other algorithms, we did more fine-grained lower bounds, for example. And then we ran classical simplex algorithm on a benchmark library, multiple benchmark libraries. We recorded the runtime. And then we ran it through this pipeline here to work out the Nanachini's number of gates Nanachini would at least need to solve the same instance. And we came up with some horrendously depressing numbers. I want to just express to you how shocking this is. So Nanachini, on paper, his algorithm has a complexity advantage over the simplex algorithm. But in reality, you would need quantum gate times that are in the order of 10 to the minus 14 seconds in order for that to outperform just a linear programming solver on a laptop. Remember what we were talking about gate times earlier? 10 to the minus 14, that's like faster than superluminal signaling is required in order to get the quantum computer to get that advantage. And how big, you might say, but these instances aren't very big. No, they're huge. 10 to the 6 is a huge instance. Indeed, we think that as your instance size gets to the 10 to the 20 or so, then the advantage might show. But for any, these are all industrially agreed libraries of benchmark instances. These dots.
This is the minimum time sorry, it needs to run at in order to have the classical algorithm be slower than the quantum.
Correct. Yeah.
Okay, very good.
Oh, because instance libraries, they have thousands and thousands of instances. They classify them sometimes into easy ones and hard ones.
So on hard ones, it does even worse.
It does worse, yeah.
I guess because the classical algorithm just has more steps.
Yeah, you're screwed by the classical overhead. So, yeah, it's a bit depressing, right?
But you're fighting against the classical one as well, right?
Yeah, we're fighting against the classical one. But we're replacing subroutines in the classical.
So are you supposing the classical algorithm runs for like a day or?
No, this is milliseconds.
No, but I mean, how are you comparing this? Are you saying like the classical algorithm takes an instance, gets a day or something, and then like what is the gate time I need to beat that?
We just track, we count the number of cycles. Sorry, I didn't say how we're measuring things here. The classical we count wall time, like how long did the clock take for the classical algorithm to terminate?
Yeah.
And then we say, okay, the quantum device wants to beat that wall time. How fast does the quantum gates have to be to beat it?
I see.
At least this fast, and this is super ridiculous fast. Yep.
How about parallelizing things?
Yeah, okay, there's an argument to be made. This is single core quantum. If you parallelize it, can you do better? Well, you can sort of, but you need to have like 10 to the 12 cores or something. I mean, you can do kind of back of the envelope arguments where it's just like you need more, it'd be far more parallelizable than the classical device. So didn't seem like a fair comparison. This is single core. It's cool. Okay, that's bad, right? If you see something like that, and we can give you more pictures like this, like for lots and lots of algorithms. But I don't care. I don't really want the bad stuff. I want the good stuff, right? So let's see. How can we beat it? How can we actually do better? So the answer is use all the information the classical algorithm has for you and use it up first, right? Don't ignore it. So this is a key mistake that anyone who writes a paper using the acronym QAOA makes, right? They take their optimization problem, they throw away 60 years of innovation in operations research, and then they're surprised that the quantum variational method doesn't get to the optimal answer. I mean, this is ridiculous, right? What you should do is you should run the classical algorithm first, exploit all that information that the classical algorithm gives you. It may not give you the optimum, but it gives you so much side information. It's a treasure trove of information. Exploit that, stuff it into your quantum algorithm, in this case, Grover, and then see if you can't get somewhere further, quicker, better, faster. Okay, here's a very silly example to give you a sense of how to do this, but it's instructive. Imagine you want to solve a binary linear maximization problem. I want to know if there's an assignment of the binary variables which gets me above V. Now, what you should do is quantum min finding. Let's pretend we don't know about that. The naivest thing you could do is just set up an oracle that gives you a 1 if you're above threshold and 0 otherwise, and run Grover. That would be very silly because it would take you in the worst, not even the worst case, like in some sort of reasonably average case, it would take you like this many iterations of Grover. Yep.
Sorry, but I mean, you should just take X to be 1 for the positive ones and not 0 for the negative.
Exactly. That's the greedy algorithm. That's what you should do, right? That's what you should do. But if you're naive with Grover, you don't do that. You don't even do that. And so the take-home message here is that you didn't even use that obvious thing that you should have set up your initial state that you're pivoting around, not to be the equal superposition, but why don't you just put in the optimal information somehow into that state and get Grover started on a good spot rather than a bad spot? And that's the difference. That's exactly what you should do. Classical greedy takes n iterations. You just run down the variables and you're done. So this is silly. This is a silly example, but here's one that's not silly, right? This is nearly the same problem. It's the Napsack problem. It's weakly NP complete. However, it's very easy in practice. What is it? It's you're maximizing a linear variable, a linear function of binary variables subject to one single constraint. It's like hypercube where you've hacked off a portion of the hypercube. And what I want to do is show you firstly some classical benchmarking on this. I'm going to show you what's the state of the art classically for solving this problem. And then we'll talk about how you might do better quantum. So this is actually new results from our operations researcher partners. They're the ones who run the classical algorithms, and we asked them, well, what's the best way to solve Napsack? So they took some libraries. They took the Yorken large instance library set of Napsack instances, and they ran all kinds of classical solvers on these libraries. They ran the greedy algorithm, but that doesn't terminate with the optimum. That just gives you a relatively good starting point. That's very fast, as you can see. Greedy is just at the bottom, but it doesn't give you the optimum. They ran cpsat, that's a SAT solver on this problem. That gives you a certificate of optimality. Not always, but sometimes. Of course, we stuck it into Gurobi. And actually, the best method is called combo. It's by Piesinger. It's the fastest way to solve the Napsack problem. It uses dynamic programming. And the interesting thing about combo is that when you get to a hard instance, combo dies in a weird way. Combo doesn't die by, well, it doesn't have a runtime error. It segfaults because it runs out of memory. So Napsack's very interesting. When you solve it, you build these gigantic tables in the computer's memory, like massive, monstrous tables. You can get to petabytes if you choose your instance hard. So often dynamic programming solvers with space, they fail in space, not time. It's a very fascinating way to fail, isn't it? Yep.
Is this dynamic programming connected to like the classical like polynomial time approximation scheme for a knapsack problem?
Not directly. I mean, I don't know the FPress.
Or is this I think it's just one where you set like a certain like if you want like an epsilon approximation, you set like epsilon 1/epsilon step size, and you just kind of approximate it that way.
Not directly related, yeah. No, it's super simple, the dynamic programming. You just solve the smaller and smaller knapsack instances by adding more and more variables to optimality by basically by brute force search. And then you tabulate them, yeah.
I don't understand two things. One is like you're not plotting anything about the quality of the solutions. It's like
Because it's to optimality,
Except for the red line.
except for the red line. These blue lines, they all got to the optimum.
Why is it saturated? What is this scale?
Because this has got to do with the hardness of the library set. So you can have hardness for knapsack is very funny, right? You can have thousands of variables, but the instance is easy. You can have, or you can have harder instance. And hardness is measured by a parameter called G.
So basically, I guess the library just has instances that you can solve with this limited amount of time.
Yeah. So what the take-home message here that I want you to appreciate is that dynamic programming, in particular combo, is the way to solve knapsack. It's the world leader. There is no faster method. And it works by dynamic programming. It uses a lot of RAM, and when it fails, it seg faults. It doesn't terminate. And it gives you the provable optimum. Like you'll give you a certificate, this is the optimum, there's no better. Now, what we thought is, well, what about applying Grover to this, right? This is sort of the dumbest thing that you should try, already starts to make you a bit worried. Like super naively applying amplitude amplification to this problem actually delivers no speed up whatsoever, because you kind of have to Grover to get into the feasible step first, and then you kind of have to Grover to optimize the optimization. You think about it a little bit longer and you wouldn't do this, but it's sort of interesting that Grover just doesn't give you a speed up already. But there is a way to get a speed up from Grover, and this is what we call the quantum tree generator. So what you do is you just deal with the constraint, you solve the constraint analytically. So you create a state which gives you a superposition over only the feasible points. That's the key bit here. There's no magic. It's just like use the fact that you already know how to solve the constraint. And then that'll give you a state, an initial state, which isn't a superposition over all states, but only over the feasible ones. So that seems like the bare minimum you should do. And there's a quantum circuit you could write out that will do that. It's sort of a bit complicated, the oracle. And then the oracle on top is a bit complicated as well. But there's nothing like, there's no magic here. It's just like, just don't put unfeasible points in your superposition. And if you run this version of amplitude amplification, I'll visualize it first, then you'll get pictures like this. So the knapsack is like hypercube, we've hacked off a corner of it. So these red dots here, they represent infeasible points. This is a 4-variable instance. And then here I've plotted the amplitude on the hypercube when you do amplitude amplification. So you start off somewhere, and then you start evolving with Grover, and then it sort of smushes your amplitude over the hypercube, and then after a bunch of iterations, you end up at the optimal. Well, you should, right? Yeah, that's I think it's Grover. I don't need to dwell on this, right? And to understand, however, the performance of Grover applied to knapsack, we found it very helpful to actually discover a dequantization of this method. And what does dequantization mean here? It just means a random walk that's biased. So we do a random walk over all feasible solutions with, and then we take a biased walk towards the optimum of this random walk. And this is sort of the analogous classical random walk for this Grover algorithm that I've just written down. And it's very handy because it gives you a heuristic way to estimate the runtime of this algorithm, even though we can't run it. Right? This Grover, we cannot run this Grover algorithm because we don't have any logical qubits. We can't even run it on IBM, right? Because decoherence kills you after 2 or 3 steps. So this is pure fantasy, but we agreed at the beginning of this talk, right, that we get to have logical qubits. Okay, and now this is the result of hard and dirty benchmarking, hybrid benchmarking applied to this Grover algorithm and also using the CTG to predict performance on larger instances. So what I want to, we'll dwell on this plot for a little bit. It'll take a while, I guess, to go through all these lines and explain these lines. And then you'll see why I'm sort of optimistic and maybe pessimistic at the same time. What have we got here? On the x-axis, we have size of problem. So we're only dealing with 600 variables, but now we're dealing with harder instances. So G is 2 is kind of hard. G is 7 to 10 is very hard instances. They got more of an NP complete problem squished into the knapsack instance. And what do we see? Cycle, what are we measuring here? We're measuring cycles. So the rules of the game that we played was, well, how do you measure the runtime of a quantum algorithm? We don't have one yet. Well, let's just say each gate costs 1 unit of time. That's a cycle. Is that fair? I don't know. I leave it to you. We can debate this to the end of time. There's always this debate. So we compare cycles of the classical device with cycles of the quantum device. Cycle of quantum device means gate, 1 gate. So we count gates. And you can use benchmarking software on your laptop, and that counts the number of CPU cycles. I mean, they're parallelized as well, 32 cores sometimes, but it's a factor of 32. And then we counted the cycles of all these approaches here. So firstly, combo. Combo is the blue curve here at the bottom on the left. See, combo is fast. It takes 10 to the, 8.5 cycles on a largish instance to give the optimal answer. What I don't plot here is memory usage. That's a super interesting thing here. It gets up into the terabytes pretty quickly. Also, then we got CTG. That's this classical dequantization of this thing. That takes 10 to the 12 cycles. We actually ran it, this classical random walk thing. It's not so great. Now I've got here some black box solvers, and this is super interesting observation that we found it very interesting. There are cleverer versions of Grover for these kinds of problems. They're called quantum branch and bound methods. Ashley Montanaro and Anderson Binus, they both have versions of this. And you might say, okay, maybe you need special solutions, let's just run that. So we did. We hybrid benchmarked it. We gave a lower bound of 1 to every Grover iteration, and we got some pretty sobering results here. So it takes 10 to the 12 quantum cycles for quantum branch and bound to give the right answer. So maybe not the best approach. What else do we have here? We have a QTG. That's just our amplitude amplification. That's not bad for these 600 variable instances on the left, like 10 to the 10 cycles. But that's just for the easy ones. So these finish in like milliseconds. Let's go to the right. This is where things get very, very interesting. So the black box quantum solver is just dead. 10 to the 13 cycles is pointless. You don't even turn it on. But now we see that these curves have crossed. So combo takes longer, actually longer in terms of cycles, to get to the optimal answer than the quantum version would. In terms of cycles, right? Gate. So let's see how many orders of magnitude we have separating these things here. So we've got like 1, 2 orders of magnitude separation. Yep.
Do you get a certificate with the QTG?
We do not. Yeah. That's fair. That's a fair question. We do not get a certificate, but we've been very permissive to the classical solvers. We said, classical solver, give us an answer that's good to within 30%. And still the runtimes are. So yeah, that's an important subtlety. We don't get a certificate, but if you have the optimal and you think you've got it, then you can put it into a branch and bound solver, and it will give you the certificate quite quickly. Because the closer you are to optimum, the faster the branch and bound certificate can be prepared. All right, so 600 variables. We predict that with about 600 qubits, gate time of 10 to the -8 seconds, quantum computers would deliver faster solutions, knapsack instances, as compared to the best classical rivals.
This is not taking into account the gate time. Or classical
Enormous laundry list of caveats.
There's a huge amount of caveats there, yes.
No, but it's something, I like it.
Okay, this is the stuff I'm allowed to show you.
Oh, there's much better stuff though.
There's much better stuff. Unfortunately, because when you work with industrial partners, they get very funny. They get funny.
The moment that curve went down, the lawyers started showing up.
No, they don't know the difference between up or down. It's just the lawyers showed up at the beginning, not the end.
Oh,
No, there's a permissions process you have to go through to release information. I'm very optimistic about nonlinear knapsack problems. I'll just say it like that. I'm very optimistic that maybe 40 variables, maybe 100 is hard to do classically. And when I mean hard, like really hard, like Gurobi doesn't terminate, dynamic programming doesn't terminate. There are instances with 60 variables which cannot be solved classically. The memory usage, how much qubits did we need to solve these? 600. Yeah.
Because you don't get a certificate, where's the greedy algorithm?
The greedy is always that's the side information we give the the quantum algorithm. So we run greedy first.
Oh, okay, yeah.
Everyone gets the greedy solution as the starting point. And then the quantum algorithm builds the greedy into the superposition by biasing Hadamard's. Like you just bias your Hadamard gates towards the greedy solution. And then you start from there. And the classical algorithms, they get told the greedy solution.
Everyone starts from the same.
Everyone starts from the level playing field, yeah.
CTG still on the right one, or is it kind of outside of the, like
Yeah, CTG here is actually faster than
it's faster than combo. And also less memory, I guess, right?
Yeah.
It's much less memory.
much less than yeah. So as a side effect, we discovered a faster classical algorithm for Napsack.
And that's why the lawyer showed up.
It doesn't give you a guarantee.
It doesn't give you a guarantee.
Yeah, so there's quite a big difference.
If I can ask about the QTG, the quantum approach.
Yep.
So does the advantage come from a scaling advantage? Do you really see sort of like a constant factor improvement because of this type of problem?
It's really a square root actually over this CTG. So this gray curve and this orange purple curve are really tracking each other with a square root.
Yeah. Because that's how you do the analysis, right? Exactly. More or less taking the square root of the gray curve.
Yeah.
Did you run kind of like when we did it, we kind of run into these problems that you always do, that heuristics are very smart and they do very tiny search steps. And then you get a square root over these search steps, but then you do many of these. So it's complex.
Yeah, so we put them in isolated. Once we gave them the level playing field initial state, we let Gurobi run by itself. And this is these algorithms running by itself. So it's not like in the end, I kind of lied with the hybrid benchmarking. There was only one subroutine.
Okay. I see.
Of course, as you're absolutely right. Like if we get to more complex problems, then you have to worry about this. You have to look inside Gurobi, and that's impossible. So, although we want to build a relationship with them. Yeah.
You just have curiosity, if you now do the CTG and then append like a branch and bound thing on the thing you get out, and I have a laptop with like several tens of gigabytes of memory, can you kind of, is this now a competitive new thing that
I
you?
believe so. Yeah. This is pretty new, like last week new.
Okay.
Well, that's the thing you should sell. Forget about the quantum computer.
Yeah.
The real money is in classical computer.
Yeah, but to be fair, like these aren't really super useful instances. To be fair. Okay, that was it really. I wanted to show you that plot. I thought that was interesting. Instances matter, hybrid benchmarking, and application-focused development where you focus on a problem type can enable maybe measurable practical quantum advantage without having a quantum computer.